Prom 9, and today's teardown is one of these. This is a pretty standard device, and I actually brought these fairly recently because I wanted some timer light things for various lights around my house so they turn on and off automatically. And they're actually quite interesting because they use a device known as a synchronous motor, and I have one here. It's not this microwave AC motor, it's one of these. This is actually pulled out of a same type of unit that the mechanics on it failed. It's an old one that was at the parents' house. It basically does the same thing, where they're kind of similar to a variable frequency drive motor, but they're also completely different in that they just use frequency. They don't use the phase of the motors. Like quadcopter motors are a good example of motors that use variable frequency drive. But these are the AC synchronous motors that use the mains frequency to determine a very constant rotation. And that's what these mechanical ones do. And they're used in all sorts of applications, mostly lighting. But we don't have the right screwdriver for it up here in the workshop, so we'll need to change that. That screwdriver is downstairs, and I'm not making a trip downstairs. So we'll open it with the wrong screwdriver type. Oh, you're going to be a little... yeah, it's going to be a little so-and-so, isn't it? And are you going to make me go and get the right screwdriver? I don't want to do that. It means going downstairs. Ugh, I hate you. The fun. Let me just pause this while I continue being lazy and fight with these stupid triangle screws. Okay, I caved. We need the triangle screwdriver. I do have one on my desk at work, but he's still on my desk at work. I did manage to get some stuff. Also, let's see how much power these things use. Because one thing I have noticed is they get surprisingly hot in this area where I suspect the motor is located. Oh good, that's not shorting out down there. What do you know? They do use a whole extra watt. They have good power factor though, mostly because they're going to be a resistance load being a motor. The voltage is always higher at this time, late at night. But yeah, they basically consume a whole extra watt adding a whole extra watt to your lights. That's one thing worth taking into account, is there are more efficient ways of driving things like this. And yeah, you can see all the things. So that's done. I switched that off because my Cliff Quick test is sitting down there with the live connections exposed, because it's got a neon relaxation oscillator plugged into it, because why wouldn't it? So now we've got a suitable screwdriver, we'll actually be able to open this thing without any real effort. But yeah, there's not a huge amount inside these things because I've taken them apart in the past, but they're quite interesting. Because what this does is this drum rotates round, and as it rotates round, there's a tiny little switch in there that when these are pushed down, they push it in and switch it on. Hey, it's still a bit warm here, where my thumb is. Feels like it should come apart quite easily, actually. I'm curious to see if there's any like resistors or anything that increase the power of this that we can perhaps modify to reduce the amount of power going through the motor. And apart it comes, and boom! Hey, 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 hey! Would you look at that? Now this is a different look to one of these compared to what I've seen before. So you've obviously got your mechanical bit, which is driven. Then when these things rotate round, and hit this switch, this switch will be knocked up like so. Seems to need a decent amount of torque actually, which pushes that down, which pushes onto this little micro switch here. Same type used in arcade machines. It's just a generic micro switch that's used in everything. And this switch on top basically forces the switch down using this. It just pushes on this little lever here and pushes it down, so it pushes the little button here. Ah, here's why he's getting hot. There's a resistor dumped right here, so there is potential for this. There is potential here to reduce the load. So, basically runs through the motor, which is geared down, no surprise. That actually is basically just looks like a normal AC motor rather than a synchronous one. So in this case, they didn't even go to the expense of putting in a synchronous motor. They just stuck in a bog standard AC motor by the looks of it. We should totally draw out this schematic because this is just so dirt simple. This is simpler than I was expecting, actually. Hey, look! Everyone remembered that video for like, what was it, like 30 of you who actually bothered watching the video? So we have our neutral and live here, much like we do in the plug, so they come in here. We have earth, which is NC in this case. It's just like, it basically just fires through the product, so you can use product appliances, but it's NC in the circuit. So we'll do it NC because it's not connected to anything. So the live basically connects, so here's our switch, if I can remember how to draw switches. So one part of it goes to the live, boom, boom, like that. Then the other part of it goes, yes, we should do the live in, live out, shouldn't we? So we've got live in, out. So that basically goes dunk. Basically connects the load straight across this switch. So this is limited by what this switch can take in current, which is 250 volts at I think 4 amps. So really it's only really load for lighting. And then the little synchronous motor basically connects to the live at all times. So you have neutral goes to the motor, which we're just doing the classic sense, as a superhero sign. Motor man, no. Goes through a resistor, and that literally basically loops round straight to the live. You can see it right there. So it literally is that simple. Now, what is the resistance of that motor, I hear you ask? Resistor, I hear you ask. Well, let's find out. And then, yeah, it basically just spins that round. It's got a ratcheting mechanism so it can't spin backwards. That's why you get the clicking when you twizzle it. When you twizzle the main dial, because this is a bit, but you can't rotate it back the other way. Not sure why they don't allow you to rotate it back the other way. So it's like a basic clutch mechanism. You can kind of see the gearing if we get it up close. But yeah, I remember the one I took apart. It was an old one from my parents. It used to be was a little more complex. I mean, it was kind of the same thing, but it was a little more complicated. I mean, it used a better motor, as you saw, because I showed you the motor out of the thing. It was a while I took it apart. Because the mechanics weren't housed here. It was just the motor going into a gearbox that was in the front part of the spinny wheel. So we will measure our resistance, our resistor toll, which is just make sure the fluorescent light isn't getting in the way of the display. That'll do. That's between live and neutral. I don't know why I was looking there, but hey. That is 46.7 kiloohms, so 46.7k. So if I have a pen handy, where did the pen go? 46.7k. So that's where most of the power is going. It's being dumped as heating into that. So we do have options of reducing that load. We could even do the maths to see how much voltage is dropped across that resistor and thus how much power. Shall we do that, children? I think we should. So we have 233 volts, which is kind of pretty standard for, I think. Why is my calculator not working? Hello, McFly. I think the plug's just being dodgy. I'll get another calculator. Good job I have a whole collection of them sitting behind me. And they're all super ancient vintage ones. Because super ancient vintage ones are cool. So I'll brush the dust off the display because dust is the mofo you can't escape. Yeah, you can see that display. So, 233 volts divide 46.7k, that would be 46700 ohms equals, really, 4.9 milliamps? That's bugger all. And then we get the wattage that's doing. Yeah, you basically got 4.9 milliamps. There's not a lot of current going through that resistor, but, well, power is really resistance and current together. So, if we times that by 233 volts, we get 1.16 watts. So yeah, decent wattage there. And it goes reoccurring. Well, technically 1.1624863 watts. And do we have anything further? No, we don't. We don't have anything in the final 8 digits. So yeah, that is why that little resistor gets hot. And that actually rolls up with what we were seeing on the Hoppy power meter as well. Most of the power this thing consumes is burnt away on the resistor here. So if you wanted to do a more efficient power system, you would have to use something like a capacitive dropper in place of the resistor. But then of course you run into the problem, are you dropping the voltage too much? But it's really just the total power dissipation you want to drop rather than the voltage. But yeah, thanks for watching. Hope you enjoyed. That was, it had a few surprises. I was not expecting it to be quite as rudimentarily simple as it was. But that's how things are built these days. Down to a price and cheap.